All right, so this is easy peasy chapter feasy. That's chapter 5. And just it's very common English. Okay, anyway, so let's start. So the very first question is just asking which linear models below are multiple linear regression. This one is the classic single, single linear regression, single regressor. So nope. Here, I guess the relevant contrast is between 2 and 4. So notice the difference between 2 and 4 is that 4 has an intercept, but I've never heard multiple linear regression defined as depending on an intercept. So 2 and 4. So 2 is very uncommon to see, but that is multiple linear regression because we have 2 observations for, or 2 measurements for each observation. We have some X variable and some Z variable. So there's that. 3 is really the only interesting one, I think. So the way, here you see that there are 2 measurements made, but they get turned into 1 variable. So this is, I'm pretty sure everyone would call this simple linear regression. And the way that I thought about it, put some, to use a non-vegan metaphor, to put some meat on the bones of this example, is like, imagine we wanted to predict married couples' happiness levels based on an income differential. So that's what you can kind of imagine this. Imagine like XI is that couples, is like maybe we're going to assume they're heterosexuals, I guess, because I'm going to say that this could be the man and this could be the lady. And so you might want to see if, happiness is based on that for something. And so anyway, I don't know if anyone has any thoughts about that, but if I guess speak now or forever. Silence. Yep. Okay. No one has anything to say. So, okay. So it's that. Bam. 1 done. This one, I don't even know if this is interesting enough to say. It's just animal diversity is linearly related to latitude, but only after controlling for plant diversity. So we have, I use flora and fauna because I'm just a big fan of those words. So we have animal diversity is linearly related to latitude, but only after controlling. So that's what this beta encodes, and the fact that it's going to be a linear relationship, but only after controlling for flora. So plant diversity. Done. All right, moving on. Okay, this one also I don't know if anyone did these problems and found like something pedagogically just mind expanding about it, let me know, because I felt like these were so basic that I was just like, these are trick questions and I am missing something.
I agree. I agree with you. I was like, okay, this kind of was like introductory econometrics, or maybe whatever it's called in other disciplines, it felt like. So I might have been missing something too, but I didn't feel like they did seem a little bit simple.
I'm glad you're going through them, because something about this chapter just doesn't fit my brain. And the first time I looked at these questions, I was like, what is he talking about? So I'm really glad you're going through them. I think I get it now, but this was something about this chapter. I think I have a lot of experience with regression, multiple regression, but the causal part of it and the DAGs is all new. And some of the language is just new for me. So I appreciate it.
Oh, well, yeah. Laura, did you want to say something? I saw you unmuted yourself.
Oh yeah. I was gonna say the causal stuff, Ken, was kind of weird for me too, because like in standard linear regression, we're not used to, like, at least for me in my college, we didn't, talk about, it was always like correlation is not causation. And even what I picked up, maybe we can discuss this later. I want to hear your guys' thoughts about this, is even those counterfactual plots, which are supposed to help you tease out causal inference controlling for other, factors, it still doesn't really cause per se. I mean, it kind of depends on you setting up the model a certain way, it seems like to me. Maybe I was missing something, and that's why I'd love to hear another perspective. And then he had all those caveats about like cause is how you set up the problem. I don't remember the exact words. I could go back and find them, but I don't feel like I walked away with a really good understanding of like, okay, is this cause or is this just like a methodology we can do?
Well, yeah, if we want to get into that now. So I have not had the most thorough reading of this chapter. So Laura, I'm not going to be able to help. But if we want to, oops, did I just close out of something? I think I did. I have to start a new share. In any case, but if we want to, I don't know, does anyone have any thoughts about the counterfactual stuff?
I didn't get that far, but I do remember him saying something like, I think the idea is that the causal explanation is the science, and that informs the model, and the model can support or reject that maybe, but you can't prove causality from a model.
Okay, so that I'm glad to hear you say that, because that was kind of what I was thinking. I just found this statement when he introduces counterfactual plots. A second sort of inferential plot displays the causal implications of the model. And I think that's what you were saying, Kent, where it's like, if this model is flawed, then any causal implications you draw from it will also potentially be flawed, which was kind of
That makes
scary, I
sense,
guess.
yeah.
I think though the question to ask then would be like, what is the I think the idea is that you can imagine a kind of, you can do a complicated situation where you have observational data, and he mentions that one thing that you can do is write out your causal model, your directed acyclic graph, and realize, for example, that maybe the empirical implications of my model aren't what I thought they were. It might have no empirical implications, depending on maybe a complex web of confounding that could be like the opposite of what I thought. I think that's the point. I mean, he mentions at one point, he calls them like a heuristic. So I don't think, and they just really encode like this thing positively affects this thing. There's no like, is it a linear relationship? Is it quadratic? And stuff like that. So I don't know. I know that DAGs are a big deal though. No, they're in vogue. So I'm glad that we're seeing them.
I've never used one before, so the little packet, the R packages are really helpful, and I'm curious to hear his rules that he gives for, to figure it out next chapter. But yeah, I've never seen him before this.
Oh yeah. Maybe it's just, so there's been like this flurry of causal inference books that have come out. By flurry, I mean like less than 5. But anyway, for the social science world. All right. But maybe, well, okay, if we want to talk about it more, I'm not going to prevent that. But I think next week, after I finish reading this chapter and then read next week's chapter, I feel like next week we can maybe get into it a bit more. This one, I'm just going to skip the third one since
Actually, I have a question about this one.
Sure.
Because what confused me is saying that neither parameter alone is a good predictor, and that there's no way to reflect that in the model, right? It's just that you need to make a multiple regression model. So it confused me that there was like too much information in the question, or more information in the question than you can actually reflect in the model.
Yeah, exactly. I think maybe if you wanted to be, super stickler about it, what you would do to just translate literally everything in the question is you would show this, what I'm currently, hold on, I need to actually share my screen.
No, you can see it. It's shared.
Good. Oh, right. For some reason I thought, anyway, well, I'm glad I wasn't doing anything embarrassing then. So you would just write this down. So time to degree, and a simple linear regression where this is funding, I think, right? What is it? Yeah, funding. Yeah. And then you would say like comma, beta, $, equals 0, or is indistinguishable from 0, right? You show that, then you would show this as this simple regression, which I can't highlight it all at once.
Right.
Show that that's 0. I mean, I guess that's what you would do. But yeah, you're right. I don't think there's any. I mean, one thing I thought you were going to say, Ken, is actually, I don't know how this situation is possible. That's another thing I was going to say. So I just from very limited experience, it seems like funding and laboratory size would be positively correlated. So if these two variables are pairwise positively correlated, both are positively associated with time to degree, which is stipulated in the question, which is actually a relationship that I don't really understand. Like, I don't think this situation is possible. Because in
Maybe
fact,
not.
if these two things are related in the real world, as I think they have to be, funding and lab size, and you actually run this simple regression, this, instead of being biased towards 0, will be biased upward. So that was my actual question with this problem, was like, I don't know how it's possible.
I guess
Not
you
a
could-
PhD student, but just intuitively, it doesn't really make sense to, it seems like the more funding you'd have, like, and you'd be able to complete your PhD sooner, but
That's
Yeah.
what I thought too.
yeah, so I was like, I mean, I guess if you just like hang around as a PhD student and they don't want you to graduate, like your advisors, because you keep doing all these like useful experiments and, you know, helping with papers and such. But again, I don't know how the real world works in that regard.
Yeah, so a lot of
Can-
mysteries. Go ahead, Federica.
I was saying, can you put an interaction term?
You could, I mean,
It says neither amount of funding nor size of laboratory is by itself a good predictor of time to PhD degree. But together, these variables are both positively associated with time to degree. So I'm just saying, maybe they together are influencing the time to degree.
yes, I'm trying to think. So, although if it were only the interaction, then, well, I guess one reason, kind of what in English language test taking terms we call a context clue for that, it not being an interaction, is that we haven't covered interactions yet in the book. So I don't think he would have us consider that. But also, if it were an interaction, that would at least allow for the possibility that like one of these is negatively correlated with time to degree, conditional on a certain value of the other one. So it's just a more complex situation. I mean, that's just what
Yeah,
the
but
logic.
it says they are both positively associated. What are positively associated?
Yeah. So, I mean, no, I mean, definitely, I mean, who knows, maybe in a future chapter, we'll find out that, but I guess my reading of it is just that the easiest way, and the way that is also reflected in what he talks about in this chapter, is just to have both variables, funding and lab size, be positively associated. So it's this greater than 0. So both together in the same model. That's what I think he means by together. But, you know, I hadn't thought about that, but together could be some strange combined index of funding. So that could be, it could be this situation. I hadn't thought about that. So I don't know how you would combine those two. It actually wouldn't be that difficult. It could be like some type of materials funding plus graduate student funding as a way of, anyway. So you're right. I hadn't thought about that. It could be these things, but I just feel like he meant this, I think, even though, as now Kent and Laura and I have discussed, it seems like either an impossible or very strange situation, which maybe he did that on purpose.
Be interesting to try to do some simulation and make up some data that actually fits this description.
That can be your homework, Kent.
I think my homework is getting through chapter 5.
All right, I'm going to finish this off because I feel like people have more
let's
interesting
go
things to talk about. This one was actually by far the most interesting of the easy questions, so that's why I'm going to spend the least amount of time on it, apparently. So we have a 4-level factor variable or categorical predictor. So the labels are just for maximal abstraction A, B, C, and D. And they have, so you can imagine a data set where you have, these are not stored in one variable, they're stored across 4. Each has its own column, right? So which are just dummy variables, or he also refers to them as indicator variables. And so he writes out 5 models, and the question is, which of the following linear models are inferentially equivalent ways to include the categorical variable in a regression? And he defines inferential equivalence as being possible to compute one posterior distribution from the posterior of another model. So well, let's just dive into it with the examples. So notice what's going on in the first model. You are predicting the outcome based on, so you have an intercept, and then you have 3 of the 4 indicator variables. So this is what R would do, for example, if for some reason category C was first, it would drop that. And then one thing I guess to notice is that what these quantities are, so what BA would be is the difference between A, so A's mean value, A's expected value, and C's expected value. B would be the similar, this beta B, with the difference between B's expected value and C's and D's. So that's what, so your posterior distribution, the posterior distributions you would have would be on all your 4 parameters, and these would be the differences. So these things here. All right, but so first we need to say, like, all right, so that's just what the first one is. The second one, I think we can go over really quickly because I'm pretty sure this model would just fail. Like, I don't think you can even run this model. I don't think you can run it in LM. I don't know what would happen in a Bayesian situation, but the point is that there's just, you have multi-collinearity, but like a very technical, just literally like not even near multicollinearity, you just have multicollinearity. So I think 2 is almost like a trick question, like you just can't run that model. So I'm not going to discuss 2 anymore. So 3 is the same idea as 1, but you just leave out A instead of C. And so the question we're supposed to ask is, are these 2 models inferentially equivalent? And so again, meaning, is it possible to compute one posterior distribution from the other? And so to think about this real quick, what do we have here? So for example, that these parameters are again beta A, beta B, beta D, and the first one are differences between that category and C. And so one thought so I think in a strict sense, the answer is no, but, and I'm open, because I literally did these problems right before this. So these are like first blush intuitions. But that said, it seems like here what you could do is calculate. So for example, if I want to calculate the posterior distribution of average height of C, what I would do is add the posterior of A, and to this one, I would add these 2 together to create a distribution of mean C, I don't know, value. And then if I wanted to get the difference, I get a contrast between, for example, C and A, and this is going to be kind of redundant. Well, no, let's say I want to get a contrast between C and B. I could actually do that. Then I could just add these 2. Oops. I could add these 2 and get that specific contrast. And you can really do that in any case, but I'm not sure that that's the right answer. It seems intuitive, but it could be kind of weird and hacky and wrong for a technical reason that isn't obvious at first blush. So I don't know if anyone has any thoughts about that.
I think they're equivalent. I mean,
so, but do you think that they are? So this is like the real thing that the reason I don't feel confident in my answers, except for when it's like, I think it's impossible. It's just this possible to compute one posterior distribution from the posterior distribution of another model. That's my that's where I feel like, I'm new enough to this.
So this is, we're looking for the posterior distribution of the parameters.
Exactly. But so notice that in a very literal sense, these models have different parameters. So for example, there's no baked into the, like, QAP or BRMS are just, in either case, are they, like, and this one very literally has this parameter B sub A for the A indicator variable. That's the difference between A and C. And here, so here, I guess, you could invert this. You could put a negative sign in front of this maybe, and then do that here, right? Because here this is, so I don't know. I just don't know. There's some technicalities.
I mean, I was wondering, is a posterior distribution referring to the mu sub I value, the response variable? I mean, if so, I would assume you'd be getting the same predictions essentially for all of the equivalent model, like the ones that don't, like 2 obviously is probably going to fail LM. And that's what I was thinking, but I wonder if I'm being too simplistic. But I do think, what you were saying, Justin, earlier, that you could derive all the parameters. And so I know that they were briefly touched on, I think it's in chapter 2, maybe 3, like adding up distributions. That was across like different response outcomes. But I'm guessing it works the same way for parameters, but I don't know that my technical knowledge is strong enough to answer that question definitively.
Well, where did you come out on number 4? Do you think number 4 and number 1 are equivalent?
Okay, great question. So again, just for the benefit of people who haven't seen this problem, what the difference between 4 and 1 is that we removed the intercept and included an indicator for each one. So now, for example, let's just take the difference between alpha B here in the 4th model and beta B and the first model. So the difference between these two, just as by way of illustration, this would represent the model's view of the mean value for B, whereas this would be the mean difference between B and C, which is the omitted category.
So then in number 4, that will be either alpha B minus alpha C, or the other way around. I'm not sure which, but it's going to be the difference between those 2 alpha parameters.
Right. So yeah, I think it should be. Go ahead.
But then sorry. Go ahead, Ken.
I think you can look at the BA, BB, and BD from number 1 and see how to compute those from number 4. And if you can do that, you can do the same thing to get the BB, BC, BD from number 3 from number 4. And if you combine those, that tells you how to get between number 1 and number 3.
Yeah, so I think that is right. There's one really interesting, actually, it's interesting, like the way a tidbit is interesting. So he mentions that when you have this dummy variable encoding of a model, you actually, for example, the variance for this will be less. So your variance for your estimate of category C will be less than your variance for all of these, because they're actually, when you compute like your mean value for A, you're combining a prior on this plus a prior on this, which I thought was like a really, so whenever you get to section 5.3 on categorical variables, that is like a really interesting thing that I think a person wouldn't think of until actually like encoding these models. So I think so insofar as the posterior is a multiplication of the prior plus the likelihood, there's like a very technical sense in which 4 and 1 are not going to be equivalent. And again, you'll see that, it's one of these things that like I don't think you would ever think of until someone writes it down, and then it's obvious and blah blah blah. So so you'll see what I mean when you read it. But yes, I think what you said is also right, that no, I know what you said is right about being able to calculate these things. All right, and so again, I want to move on because I've taken up way too much time, and just say that 4 and 5 are literally the same, just because you can rearranged. Like AI is just this. So that's done. All right, please, someone take the floor from me now. Whoever's doing the first medium problem.
Well, I am. So I don't have a nice presentation, but yeah. Okay, so just the questions and yeah, my scribble of the solutions. So for the 5M1, an example that comes to my mind is about the Nobel Prize, the number of Nobel Prize winners per country, and then association with the chocolate consumption as well as GDP. So I find it surprising that I thought it's just something that appeared in a news or blog post, but somehow it actually got into the New England Journal of Medicine. And it's like written in a very serious way that the claim was made as if there is a real correlation between chocolate consumption and the number of Nobel Prize winners per country. And the author said, well, I can give you the link later. The author said that there is no other explanation that can fully explain this finding, which I find really surprising because I can immediately think of, well, how about the wealth of these countries, for example? So I guess that is an example that comes to my mind. So because the chocolate, yeah, I guess it's fair to say that by looking at the figure that we have here, it is indeed correlated, and the GDP is also correlated with the number of Nobel Prize winners. And once we include both GDP and chocolate, I would say that the GDP would explain most of the variation. And I guess, yeah, I can proceed to the next one. So if you have more interesting or intuitive examples, then please go ahead. So for the 5M2, an example that came to my mind is about the association between health, income, and medication use. So, well, I think that health positively correlates with income. So the richer you are, I would say generally the healthier you will be. And then about the between health and medication, okay, I guess I can zoom in a little bit. And health, I guess, would be negatively correlated with medication because, well, if you're healthy, then you should not consume any medication. But then income could actually be positively correlated with medication because, well, if you don't have like universal healthcare coverage, then I would imagine that maybe only the rich that can have access to the medication. So, yeah. So I guess that's an example where the outcome can correlate with either of the predictors in different way, in a different direction, and the predictors correlate among each other. And for the 5M3, well, I haven't really thought a lot about this, but an explanation that came to my mind is, well, whether divorce causes remarriage. Well, I would imagine maybe if there are, if more people are getting divorced, then they would also expect to remarry. I don't know. But I guess one of the things that we can do when we are analyzing such data is to like include an indicator variable, whether it is the first or the second marriage of a certain person, and also to yeah, so that we can know is the high rate of marriage really caused by remarriage, or is it simply unrelated people get married and completely separate people get divorced. So I guess, yeah, that's it. And a way to evaluate this relationship, I guess, by doing a longitudinal study, and then we can track across cohort. Okay, if this, I guess, generation marries a lot, are they getting divorced a lot? So really tracking each couple across the years. Okay. So I guess, yeah, that's for the 3 medium question. Okay, now we still have lots of time.
Okay.
That was very fast.
Yeah. I like the chocolate GDP example. That I just chose ice cream. That which is an econometrics textbook one, but that I had never thought about that with chocolate and Nobel Prizes. So cool.
Well,
okay, I will share my screen. Okay. Let's see here. Okay, so question medium 4. Let me read that one out. In the divorce data, states with high numbers of members of the Church of Jesus Christ of Latter-day Saints, also known as LDS, have much lower divorce rates than the regression models expected. Find a list of LDS population by state and use those numbers as a predictor variable, predicting divorce rate using marriage rate, median age at marriage, and percent LDS population. Possibly standardized. You may want to consider transformations of the raw percent LDS variable. So basically what I did here, I just included this since if anybody is interested in doing it themselves, I literally Googled LDS population by state, found this handy little website, just a very easy web scraping with had a table. It had what I could use to calculate, did a left join, everything worked out okay. And then let's see, so P is the standardized percent. D, of course, being the divorce rate. And then what is, yeah, M is age at first marriage, of course, is M, and then, or marriage, and then marriage rate is M. A is age at first marriage, M is marriage rate. So let's see. Here I am plotting percent versus, oh great, I've got to run this again. Okay. Hopefully this will all work. I think I reused variable names, and I probably should have done that. But anyways, the point is P is not necessarily a linear relationship. So that's something to kind of consider. I do a log transformation later on. So here I have the first LDS model where I have the data D and then Gaussian family, and then we're kind of throwing everything in there. So just doing like multiple linear regression. So the priors, I haven't quite, so in the tidyverse guide, the author mentions that he will talk about a way to have different priors for like the different different coefficients. I personally have not seen that yet. Maybe I've rushed over it, but I figured, well, this seems reasonable. I don't really, the prior will get updated with the data. So then I say the LDS model, posterior summary. Let's see. Okay, website. See if that'll work. Scroll down. Or maybe not. Oh yeah, here we go. So here we have the intercept. And then age at marriage is negatively associated with divorce rate. No surprise there. Marriage rate is positively associated, but the standard error looks pretty high. So basically probably insignificant from a classical perspective. And then this is the percent of this of LDS per state, and not surprisingly negatively associated, right? Any questions? Anybody want to interject, have a different approach that they thought about that they think could have improved it? I don't want to just be monologuing the whole time. So, and then it's kind of an interesting thing. Let's hope this works this time. Good. I didn't. So this is where we do the log transformation. Now, I took the P as standardized. I standardized the underlying variable, and then I converted to logs. Theoretically, I guess I could have logged it and then standardized, but which I actually do that in another problem. So my consistency is probably not the best. Honestly, he didn't mention log transforming divorce rate, but I kind of wonder if maybe that would not be a bad idea. Because yeah, you can kind of imagine this as linear, but you got a lot of like outliers over here that to me suggest more of a log relationship. Any thoughts about that?
If you log transform a standardized variable, aren't you going to be trying to take logs of negative numbers?
I don't think so. As long as the underlying, you do the log transformation. Let's see what did I?
Oh, you did. I thought you said you did it after you
let's see. What did I
standardized.
do? I did log GDP. I guess I did not standardize it. My bad.
Okay.
I'm forgetting what I
Okay.
did. So thanks for calling me out on that. I guess I need to take better documentation. But yeah, so you can hear where I'm mutating all these variables. Because yes, you are correct. If you standardize first, if you're going to standardize, you need to take the log and then standardize. Otherwise, you can't take a log of a negative number. Okay, so now what I did here, I'm saying, okay, let's try logging using a log variable. So it's pretty much the same kind of thing. And then you can, let's try this out. So let's see, log P. I mean, this estimated error is pretty high relative to the magnitude. I'm not sure if we're supposed to be thinking about that from a Bayesian perspective, but in terms of confidence intervals, it talks about how those are misinterpreted. But you notice that there's a lot of spread here.
And that includes 0.
It does, exactly. I'm not sure if I was supposed to say that because I know he has said confidence intervals are not always, you don't always think of it the same way. So that's a pretty big distribution, which does include 0. And then age is highly significant, definitely has a negative effect. Marriage rate, again, could be 0. And yeah, so even though it looks to me like there is more of a log relationship between divorce rate and percent LDS, I'm wondering if maybe that's not the best way to capture it. And then I just included this, you can predict from the model. I don't know that that's, I could run that, but it's not particularly informative unless you're trying to do more analysis. So
did you try to decide whether this actually makes a better model? Does it improve the predictions to include the LDS percent?
I did not go and compare. I should have probably, but honestly, I just did the memo of what he asked. So that's probably a good idea. I should probably be thinking a little more expansively beyond what the question says. Mm-hmm. But yeah, you could compute the fitted, obviously you would just be doing, I guess you could compare the predictions to what it actually was, see which one had the lower forecast accuracy and, proceed accordingly. Of course, that's the whole overfitting phenomena, perhaps, that we talked about in other areas where unless you have another set of data, another year, well, who knows? Any other questions, corrections, comments about medium 4? Okay, I did not do medium 5. It looked interesting, but I just didn't really have time. So we'll skip ahead to the hard one. So there, if you're looking through the tidyverse, and a note, I think people might have seen this in the channel, but for whatever reason, the hard questions that are in the hardcover of the book are different than this PDF. And I actually think the PDF questions looked more interesting in hindsight. By the time I realized that, I'd already kind of dug into the book questions. So, you know, I just thought I'd stick with it. So anyways, H1, there's two different packages you can use. There's the Dagity package and GG Dagify, or maybe it's Dagify. I honestly liked, even though this is maybe not quite as tidyverse friendly or whatever, I liked this because it was really easy to call the implied conditional dependencies. So question 5, H1 reads, in the divorce example, suppose the DAG is marriage rate affects age at marriage, which affects divorce rate. What are the implied conditional independencies of the graph? Are the data consistent with it? So this is where I got a little tripped up, because you call this, so this basically means, if you've gotten this far in the book, divorce rate is independent of marriage rate, conditional on age. Now, interestingly, so then I put here divorce, that, or in other words, once we know the median marriage age for a state, there is little to no predictive power in also knowing the marriage rate in that state. So this is, if you looked at the book, this is the same conditional independence that was discussed in the text, which, if I recall correctly, McElreath found that to be most consistent with the data. Now that is weird to me, because the idea that marriage rate affects age at marriage affects divorce rate does not make sense per se, like from an intuitive perspective. So I don't know if the point of this was to say, hey, you can have a DAG that is technically consistent with your data, but it doesn't mean you've necessarily established the causal flow correctly. Any other interpretations of that, if anybody has worked on this problem?
That sounds like a really good interpretation, that the different models can have the same, can be consistent with the data. I think that's the point he's making.
Yeah.
A couple of times in maybe it was in the video, that you can't use the model to figure out which of those DAGs is correct.
And I'm, as somebody who could be designing causal models in my future, that is a little scary to me. I don't mean like really scary, but like you could have a totally wrong chain of causation, right? But because it implies the same as actually a correct chain of causation, and then you would be, thinking that your causal model is correct because your data look consistent with it. But I guess that's the whole point, is that you have to tread very carefully. Okay. What time is it? It's 1:45. Okay, so I'll move on because I got 2 more questions and I think we're going to be. So question H2 is, assuming that the DAG for the divorce example is indeed marriage rate affects age affects divorce rate, fit a new model and use it to estimate the counterfactual effect of having a state's marriage rate M. Use the counterfactual example from the chapter, starting on page 140 as a template. So I appreciated that he guided us to the template, because that definitely made this a little more doable for me. So I am going here, if you've looked at the tidyverse guide, very similar on the method that is shown there. So here we have the D model, which is divorce rate as a function of age. And I did not include an M here because in this DAG, we're just assuming the path goes from marriage rate to age to divorce, not where marriage directly affects divorce rate. So if anybody has a different idea that I should have included that, if we have time, I can add it in and see what we get, but that made sense to me. And then age, of course, is affected, A is affected by M. So just the BRM stuff. This is how you do it when you have those, like, I guess, nested models maybe would be the right term. So he points this out, Solomon Kurtz does in the tidyverse guide. You don't want residual correlation between these two, models, put that to false. So I didn't think I wanted that, so I put that to false. And then I just have some now you notice this whole thing, it's a lot longer, right? And I just kept the really basic priors. I didn't really think a lot about it. Maybe I should have. So we have intercept, specify your response. And you got to do that for the A model also.
Can I just ask so to PRM, there's the data argument, either there's the family argument, and the third, like what would, if you were to make it explicit, what that is, like
I believe
what
that's
is
a formula, I believe. But I have to go look at the documentation. I think there is a formula. Well, let me see if I can try to pull it up here and we can take a look.
Yeah, because I've just never seen anything like, I mean, it's containing two BF objects and set residual correlation. So that's like, whoa, that's new to me.
I'm trying to do it the tidyverse way, but I will say sometimes the whole like rethinking way seems a little bit, I don't know if any of you guys have read the tidyverse guide, but creating the plots is like, some of the plots is like the coefficient plot is a lot of work, relatively speaking. Oh, it's not BRM. I put that. Okay. I'm gonna hide this. So interestingly, okay, so it's probably formula, which normally is first. I don't know why he likes to put the data first. Gaussian, which you don't need to have that be a function prior. So a lot of this stuff is not, we aren't using at this point. Chains is four is a standard, 2000, 1000. Let's see, I guess you can use future processing file if you want. The nice thing is if you name the file, you can save yourself some time by having, I guess you would refit it with new data. And there's this ... where if I've used that before for like the max tree depth is like 10, but sometimes you might need a little bit more to get all the chains to sort of converge. So yeah. So yeah, if anybody does this and they want to, maybe next time I'll be wild and crazy data science person and put that formula first. Okay, so file. I didn't do any predictions. I should have. I was just trying to get this. So this one kind of, gosh. So I had a couple of, I guess, hiccups in thinking about this because if you standardize a variable, doubling the variable. So I was trying to think, okay, how would I go about this, providing new data? And then I found, so that I had all this, which is kind of, honestly, kind of nonsense. But so these are more notes to myself. I was like, if you have them all, the standardization, it'll shake out and you'll have the same variables. So we don't want that, right? Because we're trying to test the effect of having the marriage rate, seeing how that flows through to divorce rate. So there's a way that he shows, let me see what page it is, if any of you are looking to do these in your spare time. Yeah, so it's R code 5.23. That's of course the not tidyverse way, but basically you specify the variable you're trying to manipulate. So what you do is, I have just defined here median marriage age, and then I divide this by half. So we're trying to understand what happens. So then I create M as these two, this vector of marriage, median marriage rate, and then the halved. And then I just, to standardize it, do it by the mean divided by the standard deviation. And then A, we're holding constant. So this, holding it at 0, I was like, not sure what that was going to do, because it's like, we don't want it to be 0. But I guess the point is, we're just saying we're not doing anything with A. So then go over here to the predict. Our response is D. New data is, of course, this thing right here. Summary is false. I'm not sure what would happen if maybe that'd be true, but I don't think it gets a little messy. Convert that to a data frame. So now what I'm going to do is I set names, which is kind of a good idea to keep track of what you're talking about. So marriage rate, and then the other one is marriage half. This is all shown in the tidyverse guide. And I would recommend you walk through the steps yourself just to kind of see what each thing does. So then you want to see the difference, right? Having it, and then the mean difference. So I ran this earlier today, and I got basically, keep in mind, this is a standardized variable, basically super close to 0, which I guess either I did something wrong. That's certainly possible. However, intuitively it kind of made sense, right? Because we were looking at how little the marriage rate seem to have any impact when you accounted for age, right? So it's basically saying a lot of that is the divorce rate is changes are coming from changes or differences, I should say, across states in the age at marriage. And going back to our DAG, where we did that, what does that imply? It did say divorce is independent of marriage rate, conditional on age. So maybe I'm not off here. So in other words, most of the effect on divorce is felt through age, and there's little useful info we can gain by knowing marriage rate. I'll stop there. And then before I move on to question H3, I'll try to go through that quickly. Any questions or corrections, comments about the way I approached it? And yes, I should have graphed more. I realized that I don't like to make a graph unless I absolutely have to. It's a little, I'm being a little lazy, but hopefully you can forgive me that.
Back, you mentioned holding A at 0 when you created I think the tibble to generate the predictions. Wouldn't that just have the effect of holding, it's like holding age at marriage constant at its median value? Like that's just what that would like mean. And
I think especially say you were not going to change age. I think so. And like I said, it wasn't all totally intuitive to me, but I did try to take his advice and follow the template. And if you look at that code chunk, he definitely uses 0 and the tidyverse guide. So at first I thought, should I just put in like the A model here, which was whatever that was, like, and look at those coefficients? It didn't really seem to make any difference when I did that. So yeah, I'm not certain I really have an inner understanding of the workings of how predict interfaces, but I certainly followed the outline that was laid out for us.
okay.
Do you want me to, if you want me to try doing it, we can see what happens.
No, no, don't. Or do, I don't know. But anyway, it's probably a small question. I need to really get on this tidyverse guide.
Yeah, and this is even if you do like a data frame using the regular way, he still has A equals 0, which I was like, it just, again, that kind of wrangling is like, well, if you think that marriage rate affects age, then are you constraining A to be 0? But maybe it's more like saying, hey, we're going to see the direct effect because we're holding that at 0 of just changing marriage. It's basically saying, hey, if you change marriage rate, it's not going to impact divorce rate because we've already got A in there. That's the best I came up with, but perhaps there's more. So, okay, I'm going to try to make this quick and only have a few more minutes. So this is the milk energy model. Suppose that the true causal relationship among the variables is M, which is mass, affects neocortex percent, which affects the kilocalories per gram. However, M also directly affects kilocalories per gram. So he says, now compute the counterfactual effect on K of doubling M. You will need to account for both the direct and indirect paths of causation. Use the counterfactual example from the chapter, starting on page 140 as a template. So this one, I was a little bit tricky because I'm like, okay, page 140, I guess we had sort of multiple things going on. I looked at the tidyverse guide. So here's the milk package. I just standardized some stuff. And then I created the log mass, which I standardized myself right there. And then drop NA is the tidyverse equivalent to complete cases. So when we do that, we only have 17 observations because 12 of them were like, I guess, did not have complete cases. So you're probably starting to recognize this by now. And this is what I was referring to, not using the underscore. It was kind of a pain. So this is the whole, hey, kilocalories are affected by both the log of mass plus the neocortex percent. And then the N model is basically saying, so log mass has a direct effect and then an indirect effect, right, through neocortex percent. So you recognize this by now, I'm sure, right? Going through all this. Yeah, it's a lot to type out, honestly. I don't know why I thought this had some sort of intuition that this would take more time. So I increased the number of iterations, but everything came out okay. So now he says, what is it? The doubling M. So here I'm changing, well, my name is log mass here. So basically doing this, which hopefully I didn't make any mistakes there. I probably have to go back and think about that in terms of, so I followed that same predict milk mod, the response. This is a response we're interested in, not the neocortex, right? That fine. Mass 2. Oh, let's see. You know what? I realize I actually need to. Oops. The order I had up here was 2. Well, you guys are seeing me correct stuff in real time. Guess I need to be a little more detail oriented on that one. So, okay. My mutate differences. Well, I guess yeah, mass 2 minus mass 1. So let me run that real quick. Yeah, so it didn't make much of a difference. So yeah, not surprisingly, this is not, I didn't do any confidence intervals or anything, but this is a mean over like some prediction. So we're kind of simulating in a way, and this is not 0, right? So it's saying that this is like the effect of doubling mass. And supposedly, I do not know much about primate milk, but the law, so mass, a higher mass of an animal is associated with lower kilocalories per gram, if I remember correctly. So I guess this kind of makes sense. If we're doubling mass, we think that it affects kilocalories, that we would expect those to go down. Any questions? I see it's 2 p.m., so I won't go on too much more, but any questions, comments, corrections, different ways you would have approached it? I don't hear anybody.
No,
For me, honestly, I still need some time to digest it. So yeah.
Oh yeah, sure. No, I mean, I'm sure that there's definitely ways that I could have improved it. And ideally I would be doing more graphs and do a counterfactual graph. But if you've seen the ggplot code it requires to make those counterfactual graphs, I was like, no, I'm feeling lazy. So I'm just gonna be honest with y'all. I was like, I want to get to the answer and move on to the next problem. So that was kind of, but if anybody wants me to send them this, I don't know how we're incorporating question responses, if we are in like a book guide, but I can send it to you. And if you have any questions, things that you have insight on, corrections, other ideas, I'd be certainly interested to hear those. So if you want that, just let me know.
yeah, I was wondering about that. I put in a pull request with my first set of answers back in chapter 3, I guess, but I don't think any of the other answers have gone in, and do we want to keep doing that? So we make our own answer guide?
I think it's tricky because some of us, our RMD files probably overlap. Like, for example, if I just submitted my RMD, I did a couple of the same questions as Michael, but, he was the one presenting, and I think he put more thought into it. So I guess maybe we'd be okay with having multiple ways to do it. It's probably better than, I don't know how that would all get like reconciled in GitHub.
Well,
I'm not
just
honestly really sure about that.
You have to fork the repository and incorporate your answer into it. So it's a little bit more than, you're basically taking
Yeah.
the guts of your RMD and adding it into the repo.
Yeah.
And then doing a pull request. So if multiple people did it, we would just have multiple versions.
So yeah, I guess you're right. That wouldn't be a bad thing, probably be a good thing, actually.
Yeah, it would be work though.
It's work for the presenter and also work for the two moderators to handle the poll requests.
Yeah, I don't trust the moderators, to be honest.
They're sketchy for sure.
Yeah.
So I guess
Uh,
that's a no then. Does this have some other way of sharing? Because I was interested in some of the earlier answers, I think. I think Mikhail did some with the tidy base package a while ago, and I'm curious about that.
Yeah, I mean, I guess we could just, a really simple solution is like some sort of Google Drive or something that's like super non-techy, not as nice as like GitHub, but just like put your answer in a folder and have at it. You could take a look at whatever answer you want to take a look at. Wouldn't be as much work for moderators, I suppose.
I mean, we could just create new parts rather than incorporating into the document. I guess we could just make a place where people can drop in their RMDs in whatever form they are.
Yeah.
Yeah, I guess we can make a Slack thread for that. So let's say I make a thread for where you can post the answers to question 3 to exercise from chapter 3 here, and then you can just put whatever you want there, whether you either your RMD, PDF, or link to Google Drive. So at least there is one place that people
Just
can
as
just
a-
easily
like
drop your solution.
Just putting it into Slack, did you say?
Yeah,
Huh. Those
I
won't,
think that's
they
the
won't
least
last very
friction.
long, but at least
Oh.
let's, because I think the free version of Slack, at least with
Mhm.
the conversations, you don't get a lot of history.
Yeah, that's true. I hadn't thought about that.
Ah,
Yeah,
Oh.
I
I
think
just realized.
the Google Drive is a good solution. It's super easy. It's going to kind of be a pile of stuff, but it's not that counterintuitive. Like it'll just be a little bit messy, a little bit ugly.
Yeah, as long as you have a descriptive name for your RMD or PDF file, somebody's looking for another way to tackle a problem, they can find what they need pretty easily.
Okay,
Okay.
sounds good.
Right.
Cool.
I guess we've gone over, so it's time to wrap it up.
Chapter 6 looks pretty long too. I was just looking at it. So that'll be fun.
So we should get started now.
I would get started. It's at 30 something pages, it looks like. And well, maybe not quite, but yeah, it's 28 pages. So yeah, it's a fair amount of reading. I think this last chapter was 30.
All right. All right. Well, I'll sign off.
Okay,
See ya.
All right.
bye all.
Bye, everybody.
Thank you.
Thank you.